In this module, we are going to do the analysis for internal flow. Internal flow typically refers to flow with some confined boundaries. External flow was where the flow was happening over a particular surface. Internal flow could be flow between two plates, flow in a triangular channel, flow in a circular pipe. Any geometry where at least there is one additional surface other than the surface over which it is flowing, that would be referred to as internal flows. Here in our heat transfer course, in our undergraduate typical heat transfer courses, we focus primarily on flow through pipes and then give equivalent relationships for flow through other geometries. So, let us quickly get started with a few definitions. In internal flows, in the earlier modules, you would have talked about concept of entrance length, hydrodynamic entrance length, thermal entrance length, so on and so forth. So, here also now we are going to use these concepts to further give various definitions, various terminologies, various real life situations, how we are going to analyze them. This is a very amongst the easiest topics or the favorite topics for students, because in fluid mechanics also flow through pipes has been extensively studied and students kind of know how to go through the problems and get closed-ended solutions. So, internal flow is very well liked by most students. So, we will use that idea of liking a particular topic to a good extent to cover something from fundamental point of view. So, we are going to talk about the concept of average velocity, mixing cup temperature, then we will talk about hydrodynamic and thermal boundary layers for Prandtl number less than 1 and Prandtl number greater than 1 cases. Then we will kind of do a thermal analysis. So, basic energy balance will be done, which will be done for constant wall heat flux case and constant wall temperature case. These two would be done. Then we will derive from first principles the velocity distribution u of r for flow through a circular pipe. So, velocity distribution for flow through a circular pipe, it would come out to be in the form of capital R squared by 4 mu d by dp by dx 1 minus r squared by capital R squared, something like this we will derive. And using this, we will derive the temperature profile from the energy equation, and from that the Nusselt number for constant wall heat flux laminar flow condition. Okay, this is the order in which we are going to proceed. So, let us first go through a few definitions, first being average or average velocity, which is used in fluid mechanics repeatedly. We will just bring it back to RAM. So, when you have geometry, whether it is a circular pipe or any geometry, if I have a cross section which is like this, the velocity is going to vary such that you satisfy no slip condition at the wall and proceed appropriately. You would have velocity profile which is something like this, if this is the flow area. It will come out to be like a paraboloid of revolution, a 3-dimensional parabola or parabola which is rotated. So, you will see like a bullet head shaped structure typical of laminar flows. Why do we need this definition of average velocity, and how and why is it important? See, in external flows, just it is a good idea to just compare a little bit. In external flows, you had u infinity and then you had local u, which is a function of x comma y, and the boundary layer was defined such that your velocity was 99% of the free stream velocity. So, you had variables u of x comma y and u infinity in external flow. Here in internal flow, if you are talking of say a circular pipe, or for even flow through parallel plates, for flow between parallel plates, what is going to happen is the following. You would have boundary layer developing all around the circumference of the pipe, and because of the fact that unlike external flow, you have another boundary over which the boundary layer develops, other solid surface. It could be a single plane. So, it could be two sheets of paper, two walls which are going to be like this. So, boundary layer will develop in 2 dimension. It could be a circular pipe where the boundary layer is going to develop in 3 dimension and flow inward from all sides and merge at some point. That point where the boundary layer merges, we call it as the hydrodynamic entrance length or entry length. This is the hydrodynamic entry length. And after this, we were told that the velocity profile would end up being something like this. This is u of r comma x. The coordinate direction is r and this is x. So, you are told that this is going to be like this, and we are having different velocities at different radial location with maximum velocity occurring at the center. The boundary conditions would be u is equal to 0 at r equal to capital R, and u is equal to u max or du by dr at r equal to 0 is 0. That means, at the center line, it would represent the line of symmetry or the location of maximum velocity. These two boundary conditions would be used in the Navier-Stokes equation to derive the velocity distribution. Okay. So, now why do I need this so called average velocity? So, when I have a profile which is like this, when I have a profile which is varying in the r direction, yes, u of r, for me to use in calculations, a velocity, it is kind of very difficult to go on looking at local velocities. So, what is done? Concept of average velocity. Water flows through a pipe with a velocity of 2 meters per second. The 2 meter per second is this quantity which is average or mean velocity. This u mean is, it is given by various symbols u or v mean or u bar or v bar. We will stick with subscript m because bars would be used in turbulence flow and the connotation may be slightly different. So, we will use u bar m or v bar m. So, mean velocity, and what it is nothing but applying conservation of mass for this velocity profile and conservation of mass for this constant velocity distribution. So, when the velocity is constant, mass flow rate is rho times cross sectional area into m bar. This cross sectional area for a pipe is pi r squared. It could be for other geometry, if it is a parallel plate, b into h. This is the h is the separation between the plates, parallel plates, this is h and b is this width. So, it could be anything. Okay. So, appropriate area is chosen. This is for circular pipe. Um is this number that we are trying to calculate, and that in effect is equal to integral rho u of r dA integrated over the cross sectional area. This dA for a circular pipe is 2 pi r dr. It is basically analogous to a strip at a location r from the center. The strip has a thickness dr. So, the area of the flow is nothing but 2 pi r, which is the circumference of the inner ring, times the thickness dr. So, 2 pi r into dr is your cross sectional area of flow, and velocity through this cross section is some arbitrary u r, whose functional form we are going to derive, but it would be known for a given problem. So, if I assume incompressible flow, I am going to cancel rho's u m bar is equal to rho u of r 2 pi r dr, r is equal to 0 to capital R. We are doing this for a circular pipe. You can do this for any geometry. For any geometry, let us say its flow between two parallel plates. This is width B. Okay, this is the two set of parallel plates for which you are doing. We can talk about a strip. This is the green strip of thickness dy, and dA is nothing but B into dy, and you, based on your coordinate axis, a u dA is integral u dA is nothing but B into u dy, y is equal to 0 to h if this is your starting axis, or minus h by 2 to plus h by 2 B of u dy if center line is y equal to 0, if y equal to 0 is bottom plate. So, this is only mathematical changes, the concept remains the same. You fix the area, or you take the area that you are concerned with, have a rectangular element in case of this geometry, in case of a circle is 2 pi r dr. So, cancel rho, I am left with u m bar is equal to 1 by a c integral 2 pi r u of r dr. A c is pi r squared. So, this is nothing but 2 pi divided by pi r squared, 0 to capital R, r u of r dr. Therefore, bulk mean velocity for flow through a circular pipe is 2 over r squared r into u of r dr. So, this is your expression, and if it is non-circular geometry, u bulk mean is equal to, in general, you can write it as 1 over cross sectional area integral over the area u of u variable into dA. So, for non-circular pipes, non-circular pipes. Okay. So, similarly, the concept of mixing cup temperature or average temperature is needed. Mixing cup temperature or average temperature is referring to the energy content that is going to be there associated with the fluid. So, energy content associated with the fluid is nothing but you have the enthalpy which is carried by the fluid through a given cross section, and because this, I think everybody is comfortable and can understand this. This is my temperature profile T of r comma z. This is my center line T of r comma z, and this refers to my wall temperature T wall. This is my r comma x or z. My heat transfer is associated with the temperature difference between the wall and the fluid, or the enthalpy carried by the fluid is m dot, energy carried by the fluid is m dot into local enthalpy, which is m dot into Cp into T. But the problem is, because the temperature is varying, every elemental strip here. So, this is the same concept. So, this pipe, you take a ring of thickness dr, This ring has a particular temperature, it has a particular mass flow rate which is given by dm dot, it has a temperature T of r comma x. This times the specific heat is the energy content of that ring integrated over the entire cross sectional area. You get the total energy content that is basically given by some total m dot, which is going to be the same as what is obtained by integration. This is your mixing cup or bulk mean temperature or mixing cup temperature. That is nothing but integral over the area dm dot Cp T local, which is r comma x. Okay. So, this now m dot total for the whole area is going to be rho u bulk mean into capital AC, which we know is the mass flow rate, Cp times bulk mean temperature, which I am supposed to calculate. dm is rho u of r dA. So, I will put it here, rho u of r dA, Cp T of r comma x integrated over the area. So, T bulk mean is nothing but 1 over rho u bar m AC Cp integral 0 to capital R rho Cp 2 pi r dr is the area. So, I am keeping these things together. These things I am keeping together because these are variables, these are constants. So, rho cancels, Cp cancels, A is pi r squared. So, pi cancels. So, I am left with T bulk mean is nothing but 2 over u m bar r squared 0 to capital R r u of r T r comma x dr. This is my mixing cup temperature expression for flow through a circular pipe. For a general geometry, for a general case, T bulk mean is nothing but this one. So, you would write it as T bulk mean is, you can cancel rho and Cp, you would write it as integral 1 over u bulk mean AC integrated over the area u local T r comma x dA. This is what your expression will be. For a circular pipe, the substitution of dA as 2 pi r dr will work, and you are going to have this particular expression, circular pipe. Okay, what does this mean? This is all fine. What does this mean? The bulk mean temperature is nothing but what you would get if I took the flow of the fluid through a pipe, put it in an insulated cup, stir it and stick in a thermometer. So, that thermometer would give a temperature T bulk mean. Okay. That mixing cup temperature, please remember, unlike this connect students have to know, unlike fluid mechanics only, where you are talking only of the velocity, only velocity, what is there? We had u of r comma x or u of x comma y, whatever you want to call it, u bulk mean. Fully developed flow condition was du by dx equal to 0, which means u of r no change. If this was not changing, u bulk mean, which is nothing but an integrated form of this, u bulk mean constant, no change, u maximum, no change. All these, once you come to the location of hydrodynamic entrance length, from here on this is LH, U of R, U bar, U max are all constants. Okay. This is the hydrodynamic part. Now, with the for heat transfer part, yes, velocity or flow is the carrier of heat, but unlike this, because fluid is getting heated, what are the things that we have here? T of R comma x, T bulk mean u bar m, and T infinity was what it came with. We do not have to use T of infinity anywhere in internal flow. So, because heat is being added at every cross section, infinitesimal cross section, this after the merger of the thermal boundary layer, this is delta T, let us say, after the merger of the thermal boundary layer, if this is my temperature profile, this is at say x1, at further location x2, my temperature profile would be thicker, because this length is representing the magnitude or amount of heat. I have added heat to this fluid as it flows through the pipe. So, the wall temperature also would increase. So, that means this length T wall at x1, T wall at x2 would be larger. T wall at x2 greater than T wall at x1. Everybody, I hope, can understand this. This is something very important. You have to make it clear. How do you get this? A fluid comes in at 30 degrees at this location. You add heat to it at the next location, its temperature is going to be greater than 30 degrees. So, the wall temperature also is changing, temperature at every point is changing, the bulk mean temperature also is changing. So, T bulk mean of x2 is greater than T bulk mean of x1. So, the profile may look similar, similar kind of profile, but not the same profile. What is the difference between hydrodynamics and heat transfer? Here, if I took a picture of the velocity profile at a particular location x1 here, and I keep the velocity profile at any location x2, x3, x4, x5 downstream of the location x1, the velocity profile would be qualitatively, that means shape wise, and quantitatively, that means number wise also, quantitatively identical. This is very important. That means both the shape as well as the size would be identical, hydrodynamic. Whereas here in case of heat transfer, the shape would be similar, but because heat is being added to the fluid, the size of it is going to be increasing. If the heat is removed, the size of the temperature profile would decrease. Nevertheless, it is not going to be constant. If it were constant, that means there is no heat transfer between location x1 and location x2, then it is not a heat transfer problem anymore. Okay. So, this is T wall, T bulk mean, and of course, T local x2 at any y location would be greater than. So, if I take this y location, temperature at this x location and this y point, same corresponding point I take here at location x2 coordinate. So, the fluid particle at y distance or distance r from y, let us call it distance local r1 instead of y. Fluid particle at radius r1 from the center, as it moves from x1 to x2 would have a higher temperature. So, none of these temperatures are going to be constant. So, unlike du by dx equal to 0, we cannot write, this is not possible dt by dx not equal to 0, obviously because temperature is changing. So, is the flow thermally fully developed ever? This is a question which students find very difficult to understand, because velocity is hydrodynamically things are getting fully developed. But if you are talking of heat transfer, it appears as if the flow will never get thermally fully developed, and there we need to give some information, additional information to students. We say that yes, it appears as if the flow will never be thermally fully developed, but if we use the idea of a non-dimensional temperature, the non-dimensional temperature would essentially represent the temperature profile, and that similarity of the profile is what is going to be seen after the location of the merger of the thermal boundary layer. And this concept of similarity of the thermal profiles is what is mathematically going to be expressed as thermally fully developed condition. So, we can write a non-dimensional temperature theta is equal to T minus T bulk mean, okay, T minus T bulk mean, T minus T wall minus T local, T wall minus T infinity. So, we will write this non-dimensional profile in the next module. Look at how thermally fully developed condition can be shown mathematically here. It will not be this. This is not going to be the case. Then from there on, we will go on to derive conditions for derive the equation for Nusselt number for laminar flow through a pipe for constant heat flux boundary condition.